Acid-base buffering is important in living systems. This module describes buffers, how they can control pH, and how they can be prepared. An understanding of acid-base equilibria is a key part of chemistry. Here we have the equation for the ionization of acetic acid in water to give the acetate ion and the hydronium ion. At equilibrium, the system is characterized by an equilibrium constant expression. That is, the ionization constant Ka for acetic acid is 1.8 times 10 to the minus 5. And this is equal to the product of the acetate and hydronium ion concentrations divided by the acetic acid concentration at equilibrium. This allows us to calculate that a 0.25 molar solution of acetic acid has a pH of 2.67. Before watching and listening to this module, review your textbook on acid-base equilibria, or see Module 22, and know how to calculate the pH of a weak acid solution. A buffer allows solutions to be resistant to a change in pH when a strong acid or base is added to the solution. There are two major requirements for a buffer. First, it is composed of two substances, a base to react with any added acid, and an acid to react with any added base. Second, the acid-base components of the buffer must not react with each other. Therefore, in aqueous acid-base chemistry, buffers are built from a weak acid and its conjugate base. For example, acetic acid and acetate ion, or ammonium ion and ammonia. Let's consider a buffer solution built from acetic acid and acetate ion. What is the pH of this solution? As a first step, let's rearrange the usual equilibrium constant expression to solve for the hydronium ion concentration. This leads to an expression in which the acid concentration is divided by the conjugate base concentration, and this quotient is multiplied by Ka. That is, we see that the hydronium ion concentration of a solution of a weak acid and its conjugate base is controlled by 1. The ratio of acid to conjugate base concentrations, and 2. By the value of Ka. On slide 2, we learned that a solution containing only 0.25 molar acetic acid has a pH of 2.67. If a buffer solution contains both acetic acid and acetate ion with concentrations of 0.25 molar, what is the pH of this solution? If we use the equation from the previous slide and substitute in the acid and conjugate base concentrations, we see the ratio of concentrations is 1. Therefore, the hydronium ion concentration is just equal to Ka, and this gives us a pH of 4.74. There are two useful conclusions we can draw from this problem. First, the pH of the buffer is higher than the pH of a 0.25 molar acetic acid solution because the solution now contains a base. Second, buffers are usually composed of acids and their conjugate bases with concentrations of the same order of magnitude. Under these conditions, the hydronium ion concentration, and thus the pH, is controlled chiefly by the value of Ka, with a slight modification by the ratio of acid to conjugate base concentrations. Now what happens to the pH when we add 10 milliliters of 1 molar HCl to a liter of our buffer? It's easier to see what happens if we set up an amounts table. To see this table, go on to the next slide. In this amounts table, we will list the amount, that is moles, of each component of the solution before and after adding excess acid, and then give the final concentration of each component. In the first line, we list the amounts of acetic acid and acetate ion in 1 liter of our buffer. For the sake of simplicity, we assume that the equilibrium has not yet produced hydronium ions. Now add 10 milliliters of 1 molar HCl, or 0.01 moles of acid. This reacts with acetate ion, the base in the buffer, to produce more acetic acid. Therefore, the amount of acetate ion decreases by 0.01 moles, and the amount of acetic acid increases by 0.01 moles. Next, we calculate the concentrations in the new solution volume, 1.01 liters. As an aside, we show them here to three significant figures, but we would round off ultimately to 0.26 molar and 0.24 molar. As a final step, we allow the equilibrium process to turn on, and then we calculate the hydronium ion concentration. To see this, go on to the next slide. To calculate the pH of the buffer, we go back to the equation for the hydronium ion concentration of a buffer and substitute in the concentrations of the acid and conjugate base. We find the hydronium ion concentration has increased slightly on adding HCl, and so the pH has dropped slightly from 4.74 to 4.71. Adding some strong acid to a liter of a buffer solution has decreased the pH, but only by 0.03 units. Contrast this with what happens on adding 10 milliliters of 1 molar HCl to a liter of pure water. This solution would have a pH of 2. The buffer has indeed resisted a pH change. In summary, here are some important points regarding buffers. A buffer allows solutions to be resistant to a change in pH on adding a strong acid or base. They work because the weak acid of the buffer reacts with any added base, and the conjugate base of the weak acid reacts with any added acid. The hydronium ion and acid and conjugate base concentrations of a buffer are related to Ka by the usual mathematical expression for a weak acid. The concentration of hydronium ion is controlled primarily by Ka and secondarily by the ratio of acid to conjugate base concentrations. But because the acid and conjugate base are in the same volume of solution, this ratio is the same as the ratio of amounts or moles of substances. This last fact is useful for two reasons. First, the pH of a buffer solution is constant no matter what its volume. Second, to prepare a buffer solution, we need only to prepare a solution with the correct mole ratio of acid to conjugate base. The volume is not important.